starting. Okay, guys. So I'm going to give you guys all time to scan this QR code. Alternatively, I don't think anyone has their laptop here, but if you want to follow along with the talk, then I think it's the first one, or it's called Data Science for Dummies notebook or something. So like when you get home or whatever, you can go through this by yourself. It has all the code and stuff, especially the maths part. You're not going to get it first time probably, because that's how maths is. That's how statistics is. You're probably going to want to watch the recording and go through it again. So here's my quote. Data is the new oil, but it doesn't take a rocket scientist to understand it, just a data scientist. Data science is not as daunting as it seems when you break down everything into simple terms. So just a little bit about me. I have studied data science for 2 years. I did some courses online as well as a very intensive boot camp. I then did 2 internships, and I'm currently working as a junior data scientist at Sand Technologies. So let's dive right into the content. So what is data science? According to IBM, it combines maths and statistics, specialized programming, advanced analytics, artificial intelligence, and machine learning with specific subject matter expertise to uncover actionable insights hidden in an organization's data. But this is data science for dummies. So I asked ChatGPT to explain data science to a 5-year-old, and here was the response. Imagine you have a big box of different colored candies. Now you want to know which candy is the yummiest or which color is the most popular. Data science is like being a detective for candies. So you use special tools and tricks to look closely at all the candies, counting them, sorting them by color, and even tasting them if you're allowed. Then you can figure out which ones are the tastiest or which color is the favorite. So data science helps us understand and make sense of lots of information, just like figuring out which candies are the best in the box. Now, let's get on to the case for learning data science. So the number one thing that most of you probably care about is the money. You can make a lot of it in data science. According to PayScale, the average salary for a data scientist in South Africa, yearly of course, is about 460,000 Rand in 2024. In the US, it's about $100,000. You also have a lot of different job opportunities. You can be a data scientist, data analyst, data engineer, data architect, business intelligence analyst, database administrator, and machine learning engineer, amongst other things. Not to mention, you have so much flexibility. You can work in just about any industry. Some of the most popular ones are healthcare, financial industry, manufacturing, logistics, retail industry, telecommunications, automotive industry. Not to mention, you can feel like you're actually making a difference. The work that you do informs your company's decisions. You can also work in industries that help people. I mean, for example, the work that I do informs where clinics are being placed in Rwanda. So you can really feel like you're making a difference in your company. You also will likely have job security. Data scientists are in high demand, and the demand only keeps rising due to the rising amount of data being generated. So this thing that I've created here, this notebook, there are lots of nice links that you can look at and if you want to delve deeper into this. So more on big data if you want to go click on the link. This one's kind of subjective, but you get to make pretty graphs and build AI. How is that not uber fun? I legit do that in my spare time, but maybe I'm just a nerd. So now let's look at the data science lifecycle. You start out with the problem definition, then you go to data collection, you clean the data, you go into exploratory data analysis. I know these are big words. Don't worry, guys. I'll use smaller words when we get to them. Then we go to feature engineering, machine learning, model evaluation, and deployment. It doesn't stop there. It iterates and it goes around and around and around. So we repeat the cycle again and again. So let's start with number 1, the problem definition. So we're going to go through an actual case here using actual data. And once again, you can go through this in your own time if you want. So the problem definition, aka what the boss wants. This is where you figure out what is the problem, who does it affect, how does it affect them, what are you expected to do to solve it, and what is not realistic for you to solve. In our case, a government municipality noticed a 10% drop in average mathematics scores and a 12% drop in the number of students passing mathematics in nearby schools. They want to investigate the reasons driving the low scores, as well as build an app that can detect students at risk of failing so that those students can be prioritized with support immediately. So that's our problem definition. Now let's move on to the second part, which is data collection, aka the part that actually makes or breaks the project. So you know the saying garbage in, garbage out? Nowhere is that more true than in data science. So we need to find good data. I'll just give you a quick example. There were some students in university, they thought they had found an amazing model for deciding whether it could tell whether a picture was a wolf or a dog. Turns out it could just detect snow, because all the pictures of wolves had snow in them. You need to have really good data. So you need to find really good data for data science. In many jobs as a data scientist, you won't do this step yourself. It will often be the data engineer's job to source the data, but companies often don't hire separate data engineers if it's a small company, and you may end up having to do this, so it's important to know. Or if you want to build an AI model for certain purposes, you may need to collect the data. So the process is as follows. You need to decide what data to gather. Who will the data be about? Where will the data come from? And how much data do we need? Decide how long to gather the data for. Decide how to collect the data. Will you collect the data yourself, or will you find a suitable data set? In our case, we have taken a data set that already exists. You then gather the data. So here, we have decided to use a data set about the municipality students and how they perform at mathematics, as well as some other possibly important data points. So if you want to learn some more about data collection or potentially web scraping, which is a way to collect data, there's some more information on the notebook. So then now that we have the data, we move to the third step, which is data cleaning, aka weeding and tending the garden. This is where the real fun begins, because we get to get our hands dirty with some code. So first, we're going to import the relevant Python libraries and create our data frame. A data frame is just a fancy way to store data. So it's a nice little table, nothing fancy. Well, I just said it was fancy, but you get what I mean. So we import our libraries, and when you look through it in your own time, I've said what everything does. So then we load it into the data frame. Data cleaning is kind of like cleaning your room, essentially. You want to get rid of all the junk and make the room look tidy. For data, this means fixing or removing things that are duplicated, any missing data, incorrectly formatted data, or incorrect data. So to know it needs cleaning, let's first look at the data. So we take a little peek at the first 5 entries. Then we want to see, is there anything missing? So we look, nothing's missing. If there was something missing, I've linked to how you can handle that. For the next step, we need to have only numbers, not words, so that we can analyze it properly. We need to change the data type of any of the columns that have words, and we store it as something called core_df. That's just the name I gave it. You can give it any name. So I create the function, and then I use the function, and we use that later. In the next step, which is called exploratory data analysis, aka what you spend all your time on. You'll spend about like 90% of your time on this. Now, because this talk is quite limited in time, I'm not going to show you all of the exploratory data analysis that I've done, but if you want to, you can go through all the graphs because, yeah, they're quite interesting. Now, this is where you basically make pretty graphs to show what is happening in the data. You explore and you analyze the data, hence the name exploratory data analysis. This is made up of 3 steps. 1, you ask questions about the data. 2, you graph the related variables to explore those questions. And then 3, you answer those questions or make some sort of conclusion. This is the analysis part. So 3 questions you will normally always ask are about outliers, the spread of the data, and correlation. The questions I came up with for this data specifically, so here I'm just getting a list of all the different variables, aka columns, and what their data types are so that I can come up with these questions. And then the questions that I came up with for this data: are there any outliers? What is the spread of the data? Is there a relationship between health status, absences, failures, and the final grade a student receives? How do males and females differ in their maths marks? Does the student's school affect their mark? Are students at one school wealthier than another? And then finally, how are factors correlated? So let's visualize and analyze them. Are there any outliers? Okay, so a massive piece of code, and we do the box and whisker plot. You'll remember this from high school, I hope. I hope all of you went to high school. And so only really absences appears to have, so over here, appears to have true outliers. But when we deal with outliers, we need to ask ourselves, number one, is this likely a data entry error, or is it a true reflection of reality? Because sometimes you do get outliers. And two, will these outliers cause bias in my data set? So for absences, the answers to the first one is it's plausible that their students are absent 70 days a year. We all remember those kids from high school. To test that, and for the second one, to test this, we'd have to build two models. So, well, like two AIs basically, one that has the outliers and one without to see which performs better. So now we go on to the second one, which is what is the spread of all the data? This is what I spent all of my time on, so I'm not going to go through all of them because there are about 40 different graphs. But here, for example, we can see that majority of the learners go to the GP school compared to the MS school. So they're like 350 compared to the MS school. So here we're just looking at where does all the data lie? Because sometimes there'll be bias in the data or in the model because of that. Because if the model is used to seeing lots of GP learners, for example, then it may not know what to do when it sees an MS learner. That's why we look at this. Or at least it's one of the reasons. So then we look at the sex of the learners, and we see that there are slightly more females than there are males. We can also look at ages and the range of ages that there are, and a whole bunch of other things. As I said, feel free to look at this in your own time. As I said, it's a lot of graphs, guys. So now on to another interesting one. Is there a relationship between health status, absences, failures, and the final grade a student receives? So here I've plotted it, and the way that this works is that the color of it represents their health status, the size of the dot represents how many times they've failed, how far up the dot is, that's their final grade, and how far along the bottom of it, that is how many absences they had. So what we can see is that the darker circles tend to cluster towards the bottom, as well as the bigger dots. They're also clustering towards the bottom. So what we can say then is that we can see a general trend of students that are less healthy and have more failures having a lower grade, and also somewhat having less absences, it seems. Or, well, generally we don't see that many or enough absences to conclude that, but generally having lower grades. So we can say that there is quite a relationship between that. So then let's go to how do males and females differ in their maths marks? Now, these marks are on a 20-point scale, not a 100-point scale that we're used to. So the average mark, these people aren't getting an average of 10% for maths, just so you know, this is closer to 50%. So females are getting an average of 10%, whereas the males are getting, 10 points, whereas the males are getting an average of 11 points. Now, we'd have to do a statistical analysis to know, is this significant? That's just fancy words for we don't know if it really matters. Because, say, for example, it rained, that could just be, sometimes the males feel a bit different, sometimes the females feel a bit different on other days. And it's just a bit of noise as opposed to the males genuinely performing better than the females. So you have to do these weird maths things to make sure that it's genuine as opposed to just a fluke. Now, we could investigate the reasons for this further using the same technique as shown below. So here we're going to ask the question, does the student's school affect their mark? So here we can see that the GP school students get on average just over 10 points, whereas the ones that go to the MS school, they're getting a little under 10 points. So this is where you have to ask, do we have enough data to make a conclusion about this difference? But let's assume that there is enough data to make that conclusion. Let's investigate maybe the reasons why this might be the case. So one question we could ask is, are the students at one school wealthier than the students at another? Now, we don't have any data about wealth per se, but we could use internet access as a substitute, perhaps. So I'm just going to do some code to be able to compare the two schools, and then we'll visualize that. So the internet access of the GP students and the internet access of the MS students. And you can see that there's quite a big difference. The MS students have less access to internet, and if we use that as a substitute for wealth, we could say that then the MS students are less wealthy, and that may explain why they are on average getting lower marks. So which factors, otherwise known as variables, are correlated with each other? Now, correlation just means that when one thing goes up, the other thing goes up at a similar rate, or it goes down at a similar rate. So it means that it affects the other thing. So you could say, for example, that ice cream sales are correlated to hot weather. So here, if you want more explanation about correlation and the statistics behind it, I have included links there. So the things that there are strong correlations here, it's nice and color-coded so that you can see where the strong correlations are. But what we do see a strong correlation between, unsurprisingly, is weekend and weekday alcohol consumption, as well as the first term grade, the second term grade, and the final grade, as well as the father's level of education and the mother's level of education. If you go through this in your own time, see if you can spot the other correlations, the weaker ones. Now we move on to the next part, which is feature engineering, aka choosing data. This is the part where you choose what features to include and whether to add more. So let me explain what a feature is. It's something you are measuring in the data. It's normally represented in the table by a column. You can read more about how to do feature engineering and more about it in the links included, but it involves four main parts: feature creation, which is making new features from existing features; feature transformation, which is changing the features into a different form; feature extraction, which is reducing the number of features with fancy AI tools; and feature selection, which is choosing which features not to use. Feature creation. So I don't have any specific domain knowledge about student performance and can't think of any metrics that I can make based on this data. But an example I can think of is if you had shipping data with box sizes, like a column with the height of the box, the length, and the width, you could make another column that multiplies them all together to get the volume of the box. So feature transformation then. This involves changing the data type, like we did earlier where we took the word columns and made them into number columns, or normalizing or scaling the data. This is very important to help the machine learning model, and there are details linked there. So normalizing or scaling just takes numbers with very different ranges and brings them into the same range. So if one column is between 0 and 20,000, and the other column is between 1 and 5, it makes them both between -1 and 1 without losing the proportion of the values. So the reason we do this is because the machine learning model can get distracted by the bigger numbers, and we wanted to treat all the values equally. So here is a nice little picture that demonstrates what happens when you scale. So you can see before it's just making noise, but after it creates a nice clear separation and it works properly. So we will scale data just before we create the model, but I've included a guide for how to do that. Feature extraction. This could be a talk in and of itself because you have to create AI essentially to do this. I've left some details about how to do principal component analysis. That's the most common type, but essentially it's a really fancy way to take lots of features and have AI choose a few of them. But we won't be doing that as it's just going to be repeating the next step, which is a simpler version of it essentially. Feature selection. This is where we use some rules to choose features. Often we have to test the different rules until we find the most effective ones. We're going to use the simple rule: if a feature influences students' grades enough, we will choose it. We will first check for influence by looking at correlation, which I spoke about earlier. So here I've taken the final grade and I've made a column with just its correlation. Now, after a lot of testing of the models, I found that a correlation of greater than 0.15 and less than minus 0.15 was the best. So we will plot which features those are just for fun. So here I've plotted all of the features as well as how much they are correlated towards the final grade. And what we want are the features that are outside of the red lines because those have the greatest correlation. So you can see that that's age, that's the mother's education or MEDU, the failures, higher education, as well as G1, G2, and G3 is what we're measuring. So we're going to now put those all into one data frame or table. And I'm going to take out the first and second term grades because I don't want to cheat. It's kind of cheating, I feel, to have the first and second term grades. Now here's the fancy part, guys. We're going to make AI here. So here's machine learning, aka, ooh, pretty, shiny AI stuff. First of all, what is machine learning? AI, first off, is code that lets a computer think and do tasks without a human helping it. Machine learning is then a type of AI. There are lots of other types of AI. So all machine learning is AI, but not all AI is machine learning. Just for interest's sake, here's some other types of AI. So there's machine learning, which I told you about. There's neural networks, there's natural language processing. You'll be familiar with that one if you know ChatGPT, and there's robotics. A machine learning model is a computer program that finds patterns based on rules and maths using data. The general process for creating a machine learning model is as follows. You take training data, then you choose an algorithm, you train it, so it learns, you then have a trained model, and then you get results. There are different types of machine learning. As you can see, there are quite a few different types, and it can be used for all sorts of different uses. There are three main types though: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is like how we learn as children. It involves data that is labeled, so we put the answers attached. It is like if we are shown an apple and told that it is called an apple. So when someone asks us, what is this round red fruit? We can say that that is an apple because we have seen it before. Unsupervised learning is when the model doesn't have labeled data. There are no answers attached. The model will then try to group the data together based on similarities that it finds. So the final one is reinforcement learning. This is where certain values are attached to each action in an environment. Some actions are rewarded and some are punished based on outcomes. I've attached a link of reinforcement learning in action, but I must warn you all, this is not work-friendly. It is wildly entertaining. By not work-friendly, I mean you will procrastinate at work because you'll just keep watching endless videos about reinforcement learning in action. You will go down an endless rabbit hole. So we are going to now make a machine learning model, since we understand it. We're going to make a supervised learning model. So first we need to prepare the training data. And what this involves is splitting the X and the Y. The X is the input, or the data we put into the model. The Y is the output that we are trying to predict. In an unsupervised learning model, there wouldn't be a Y. So here, the Y, we are taking the final grade, and the X is everything else. Next, we need to pre-process the data before we can use it. So remember earlier when I was talking about how important scaling was? Yeah, we're doing that here in a nice little pipeline to package everything together. And then we check that everything was successful, just for sanity. And now we need to separate some of the data so that later we can test it without it being able to cheat on the test because it's seen the answers. So we separate it. And now we can do the really fun stuff, choosing the model. If you enter competitions, you will just endlessly stare at screens, choosing models, looking at the results. Yeah, this is the really fun part. But for this model, I've chosen a linear regression model because it is really simple to understand and it's not going to take ages to run. If you remember straight line graphs from high school, you know how this works. Two or more variables are plotted on a graph and a line is found that best fits the data. If you want to predict the variable, then you take the line's coordinates. This line is the model, the AI model. So you take the x, you put the x in, the x that we took earlier, and then out pops the y. So we create the linear regression model, and now that we've chosen the model or algorithm, we must train it. So here is it being trained, and after training it, we need to check its performance to see if it's worth anything. So this, I'm afraid, is the maths part, everyone. Model evaluation, aka the stats part. This part gets a bit mathsy. Please don't overlook it, because this is how we decide if it has any value in the real world. So first we're going to get the model to predict what the test scores will be, so we can see what sort of values it has predicted. This is the same function we'd use to get predictions when we're using it in real world use case. Now we're going to return the coefficient of determination. This is one of the measures of accuracy. So we get 0.13 more or less. Now let's explain what that is. The coefficient of determination is 1 minus u over v. U is the residual sum of squares, and v is the total sum of squares. RSS, residual sum of squares, is the sum of the squares of the difference between the points and the prediction of the model. So you see this graph here, where it predicts, so where the model predicts, so where this line is, and the difference where the actual point is, you take that, you square it for every point, and you add it up. That's the RSS. The total sum of squares is the sum of the square of the difference between the average of all of the y points and the actual value of the y point. So you just take the difference between where the y point is and where the average is, and then you square it and you add it up for all the points. That's the TSS. So then the coefficient of determination that I spoke about earlier is just 1 minus that first one, RSS, divided by that second one, TSS, meaning that the most accurate model you can get is 1, because it doesn't have any of the error thingies. So the closer to 1 a model is, the better. This is just a general rule of thumb though. A number that is too high should make you really suspicious of overfitting. You can read more about it in the link I've given. Our coefficient of determination was 0.13, so this isn't a great model, but it's a really simple line graph. Next, we're going to use mean square error to evaluate the model. This is a really simple formula as well. We are summing all of the squares, so we're squaring the difference between what we predicted and what the real value is. The lower this number is, the better, because there is less of a difference in the error that we have made. So our MSE is 10.79, but it doesn't tell us much because this is like a squared number. It's 10.8 square grade points. We don't measure grades in square units, so we're going to calculate the RMSE. That's just the MSE, but we take the root of it. So we take the root there, the square root, and we get 3.29 grade points out of 20. So on average, our model will be 3.29 grade points inaccurate when making a prediction. That's what that measure means. That's not too shabby for a simple line graph. But because we did that previous evaluation, it gives us two reasons to believe this isn't a great model. Let's assume that we're actually happy with the performance of our model and that we're going to give it to the boss and deploy it. Deployment, aka where it all falls apart. As developers, I'm sure you're very familiar with this part. This is where we package the model to be used by other people to make it more user-friendly. Let's go back to our use case of a school district trying to predict whether a student is at risk of failing or not. These users are not data scientists. They're not going to borrow your laptop, open up Kaggle, and start coding in Python. So we need to make a nice website app for them. To achieve this, we do something called pickling. This is where you store a model or even a pipeline for later use. Think of it like pickling a vegetable. It makes it more portable, more compact, and last longer. These files end in .pkl. So here I just pickle the model and the pipeline, because the pipeline changes the values we use. So the model basically just throws errors if you don't pickle the pipeline and use it as well. So then I also just say where you can download the files if you do this yourself. Next, we need to investigate the variables. So this is for the design of our app. We need to know what possible options there are for each variable so that we know which options to include in our app. It'll make more sense once you see the app. So we look at all the unique values. Now, because I don't have time to make an actual HTML website, I will use Streamlit. And I've included a link for how to use Streamlit if you want to create a quick Python web app. Now we can make the web app, right? No, wrong. Everything fell apart. Even though it was working just fine on Kaggle. You can see it's working fine on Kaggle, but here it's falling apart. I asked Stack Overflow. They didn't know what was going wrong. That's when you know your life is falling apart, when Stack Overflow doesn't know. So, turns out it was an issue with one of the versions of the libraries I was using. So I had to upgrade it in Kaggle. So here I check the versions of the libraries. And yeah, so if you guys want to, so this is going to predict maths grades based on a bunch of factors. So if you want to, you can scan this code, and I think it's the third link. It's the one called grades predictor link. But go ahead and put in your details and see if this could predict your final matric maths mark, or at least how far off. Just remember, this isn't a very accurate model, but it's got some credibility to it. So I'm going to go over to the app that I've created. So let's see if it can do me. Wait, I was 19 in matric. Okay, and my mom did higher education. My dad did higher education. Did I ever fail? No. I wanted to pursue higher education. Yeah, it didn't predict my final grade. But it did say that I was likely to pass, so it got that part right. So here I've converted it to South African grades, so 55%. There we go. So that's how that app works. So you see it's nice and user-friendly. This is how this is it being deployed. This is how it would work in the real world, how the model works. That's it. That's how data science works. I hope it's a little less intimidating now. Now, how can you start picking up data science tools now? Let's take a look at what data science is made up of. You can see it's kind of the intersection between computer science, maths and statistics, and domain knowledge. The domain knowledge is a really important one because people come from all sorts of fields and say, oh, but I have an economics degree or I have a civil engineering degree. How will I possibly make the switch to data science? But there's so many jobs that require specific domain knowledge where those backgrounds give you an edge over every other data scientist. I don't even have a degree, and I'm hired as a junior data scientist. So don't get too caught up in specific qualifications. So first, the actual skills that you'll need is some coding under your belt for the computer science part. You can choose any tool that gets the job done but the most common are Python and R. I would recommend Python because it's more commonly used and required on jobs, as well as a bit easier to learn. So here on this document again, I've linked lots of resources, but you can try Free Code Camp on YouTube to learn Python. You'll also want to learn some basic statistics. For this, I recommend StatQuest on YouTube. They've got some great playlists, as well as Crash Course Statistics. Domain knowledge also now the domain knowledge part, that kind of comes with experience in certain fields, or if you have a degree in a certain field. So for example, if you really want to work in finance, you should at the very least study up on the lingo and the concepts in that field. Now, once you've done these or are partway through, the best things I can recommend doing are the following. Try the 66 Days of Data Challenge. That will get you very consistent. Go through this notebook and see if you understand it, especially read through the links that I've added for additional material. Then, try to improve on the model that I've made, because it's really bad, honestly, guys. Then, get your hands dirty with some challenges on Kaggle or the local alternative Zindi. They're really fun and you can actually win money by doing this. Then, maybe try a boot camp. There are two that I've linked here, Explore AI Academy. That was really awesome. I went there. And just full disclosure, I work for the parent company, but if any of you sign up, I don't benefit in any way. I just think they're really awesome. And the other one is Umuzi. Then I've also got some information on how to improve AI models, as well as a little spoiler there. And that's the end of my talk, guys. So I've also got some speaker feedback rating thing in the QR code thing. Yay. And my LinkedIn, if you guys care about who I am or whatever. And 5 minutes for questions. Earvault.
So, if I want to become a data scientist, what kind of suit should I get? I mean, like, you're obviously wearing a suit. I'm kidding. If I don't really have any kind of programming knowledge, is there still something I can do in this career that I maybe don't want to do programming? Is there openings for people like that?
I don't think you can really do data science without any programming. I mean, yeah, the computer science is a fundamental thing. I mean, in my day job, literally 90% of what I do is programming.
Didn't you know what is analyzing the data?
So you still need coding if you're a data analyst, because you first have to code the graphs to get the graphs that you then analyze. Yeah. So you do need some coding to like create the graph and then, yeah. Yeah, in the back.
Okay, so your application here, that data analysis you did, was originally to see why kids had been failing and what have you.
Yes.
But the end product was a mechanism that actually predicted results.
Yes, correct. Okay, so in the EDA, I actually do go through the reasons for some of that. But as I said, I skipped over that because of time's sake. But so it was twofold in the problem statement. It was one, to see why the grades were lower, but two, to create a mechanism to identify students that were at risk for failing so that they could be targeted for interventions. So that app, it allows you to say, take a student, if you're worried that they're at risk for failing, you can put their details in it, and then it says the student is likely to pass, or the student is likely to fail, or the student is definitely going to fail.
No, okay, no, really cool. But how would one test that? So your measuring rod would be the future.
Yeah, so that's where the accuracy part, so the stats part. As I said, the model isn't super accurate, but you can make a more accurate one. So the future, I mean, you would have to test it in real life. So you would say, test it with 100 students, and let's say it says 20 are going to fail. You follow up with those 20 students, and if 19 of them fail, and it predicted those 19 failed, you'd say, I don't know, that has 95% accuracy. So it does predict the future, as many predictive models with AI do.
All right. Okay. So that would also depend on your information gathering process, your data gathering process.
Exactly. That's where the whole garbage in, garbage out comes from.
Is there any way to test that data, that garbage in, garbage out data, before actually processing it?
So in the EDA part, where I was showing, like there's an imbalance between the number of students from one school versus the other, that's an important factor, because that can make it biased, because it hasn't seen enough of the students from one, so it may not be able to predict the students that it's seen less of, for example. I have 1 minute left. Yes? Mm-hmm. To test if the training data was faulty. So in that case, the reason they were suspicious was actually because it was too accurate. So sometimes when the accuracy is too high, you should get suspicious. So when it's above 90%, generally you get suspicious for something called overfitting.